Hello everyone. Today I'm going to explain what is carboxylic acid. This is an introduction to the carboxylic acid, the chemical miracle in everyday life. What is carboxylic acid? Acids are substances that release hydrogen ions in solutions, making them acidic. They react with certain metals and carbonates to produce various products. And carboxylic acid is an organic compound that has carboxyl group, the COOH. And understanding this reaction helps us to use them and apply them in everyday life. Okay, these are the examples, the carboxylic acids in nature. This one, this one is the left one. The left one is a citric acid, which can found in lemon and orange. And this one is the malic acid, which can found in our body and the fruits. And this one is the oxalic acid. It has two COOH group. It's called ethane dioic acid, and it can be found in some kind of plants. And this one is the biotin. The biotin is a vitamin B, and the cholic acid is a very complicated carboxylic acid, which has a polycyclic, which is a cholic acid is an example of polycyclic carboxylic acid. And this one is the cinnamic acid, which is an aromatic carboxylic acid. And this one is the DHA, docosahexaenoic acid. And the abbreviation is called DHA. And DHA can be found in a lot of foods, such as fish. And the important and this is the importance of carboxylic acid. Carboxylic acids are crucial in various fields due to their chemical properties and applications. Here are three important aspects. The first one is the biological importance. Carboxylic acids are fundamental in biochemistry. For example, the fatty acids, the long-chain carboxylic acids are essential components of lipids in cell. For example, the phospholipid. The phospholipid is the main component of the phospholipid bilayer, the cell membrane. And they are also the precursors in metabolic pathways, such as the citric acid cycle, the Krebs cycle, for energy production in living organisms. And the second one is the industrial applications. Carboxylic acids are used to produce various chemicals and materials. For instance, the citric acid is used in the production of vinegar and as a solvent. Formic acid is used in leather processing and as a preservative. And the terephthalic acid is essential for manufacturing polyethylene terephthalate in plastics and fibers. And the third one is the synthesis of derivatives. Carboxylic acids are precursors for synthesizing a wide range of organic compounds, including esters used in flavors, fragrances, and solvents, amides used in polymers like nylon, and acyl chlorides, key intermediates in organic systems. These diverse roles make carboxylic acids indispensable in science and industry.
So now I will continue presenting about structure of carboxylic acid. Carboxylic acid have the general formula RCOH, where R represent an alkyl or aryl group. COOH is the carboxyl functional group. So let's see the functional group COOH. COOH is a carbonyl group, which is C double bond O, a carbon double bonded to an oxygen atom, while OH is a hydroxyl group, a carbon single bonded to a hydroxyl group. Both groups are attached to the same carbon atom, forming the carboxyl group. Alright, so let's see the bonding and the structure for carboxylic acid. The carboxyl carbon is sp square hybridized, making the molecular planar. And the oxygen atom in the carboxyl group have partial negative charges due to their higher electronegativity and creating a dipole moment. And for the resonance stabilization, the negative charge is delocalized between the two oxygen atoms, making the carboxyl group more stable. And this is two example structures for carboxylic acid, which is acetic acid and formic acid.
Okay, now we are going to the IUPAC naming of carboxylic acid, the systematic naming. What is IUPAC? IUPAC stands for International Union of Pure and Applied Chemistry. The first step is to find the main chain. We choose the we choose a chain which has the most seniority group, which is the COH group. And if we have multiple chains that have COH group, then we choose the longest chain. The longest chain that has a COH group. If there is a tie, then we look at the number of COH group. There's a diagram. You can refer to the diagram below. The step two is rings versus chains. If there's a choice, rings are more important than straight chains. 3. Count atoms. Pick the chain or ring with more atoms. 4. Check heteroatoms. Choose the structure with more heteroatoms, such as the nitrogen, oxygen, and sulfur. The double bonds. Step 5. Double bonds. Prefer the chain or ring with more double bonds. And step 6. The numbering. Start numbering to give the lowest possible numbers, the lowest locants to the COH group or double bonds. So the COH group, the carbon in COH group must be the carbon number 1. And step 7, name substituents. Add names of side groups and arrange them alphabetically in the name. So this is a diagram that you can refer. So the first step is to choose the parent chain contain more senior group, which is a COOH. If there's no COOH, then you have to choose uh, the most senior group. So there's and you can find a list, the the ranking of the seniority of the organic functional group. So after a carboxylic acid, I think is a sulfonic acid, and then we have the acid anhydride, ester, and then amide or something like that. Okay, now we let us look at the example one. This is a common this is a carboxylic acid which we can find in nature. It's called rosmarinic acid, and you can see that there's an ester group, the COO group, the ester group, and the carboxylic group, and the hydroxy group and benzene in this compound. So so since the carboxyl group is the most senior group, it's more senior than the ester group. So the naming, the suffix of this molecule will be carboxylic acid. So the IUPAC name will be, well, this name also includes the stereoisomers of the molecule, and you can see that there are stereoisomers of this compound. So to specify the stereoisomers, the IUPAC name will be 2R334 dihydroxyphenyl 2,2E334 dihydroxyphenyl prop 2 enoyl oxypropanoic acid. And then let us look at the example two. This for this molecule, refer back to the diagram I have shown you before. Notice that this chain has has four carboxylic groups, so it must be the parent chain. So the parent chain will be the pentane. And then there are two substituents, two complex substituents there. Can you see that? So we name the substituents, and then we arrange it in alphabetical order. So notice that methyl dimethyl. One is start from methyl, one is start from dimethyl. So you might think that this is dimethyl. It starts from D. It should be uh it should be the first one. But di is a quantifier, so we don't look at that. So we look at so both start from methyl, start from M. So we look at this methyl ethoxy. So it has E. So the difference is the E, and dimethyl hex. So it's H. So E comes before H. So methyl ethoxy, methyl. This substituent will be the first one. So the IUPAC name will be 311 methyl ethoxy methyl 123 dimethyl hex 2 in 4 inyl contain 1245 tetracarboxylic acid. Okay, let us look at the example 3. Okay, in this example, we can see that there are many functional groups in this molecule. We can see that there is a carboxyl group, the carbonyl group, the aldehyde group, the amide group, the amino group, and the ether group, and the alkene group. So for this one, we need to choose the highest, the highest, the functional group that has the highest seniority, which is the carboxylic acid. So this one will be the carboxylic acid, and the parent chain is also very special. The parent chain is called azulene, and you can see that there is a heptagon, 7-member ring, and a pentagon, a 5-member ring. They are fused together, and so this molecule is a bicyclic. It has bicyclic structure, and it is also aromatic, and this is called azulene. And azulene is very special because usually the aromatic compound is 6-member, will be six member rings. But this azulene is not 6-member. It's composed by it's composed of 5-member ring and 7-member ring, which is very special. So in this case, we name all the substituents. There are 6 substituents there, and then we arrange them in alphabetical order. So the final answer will be 6 amino 4 2 carbomoyl propyl 3 formyl 8 methoxy 7 1 methylene propyl 2 1 oxoethyl azulene 1 carboxylic acid. Okay, let us look at the last example, the example 4. So this molecule is also very complicated. It has polycyclic, polyfunctional group, and heterocyclic structure. So in this case, we have to find the the largest parent chain, the largest ring or chain that has the most carboxylic group, the carboxyl group. So in this case, the naphthalene will be the parent chain because although you can see that there is a straight chain up there that also has a carboxyl group, but this chain is only one, two, three carbon. So it is a propane. It's smaller than the naphthalene ring. So the naphthalene will be the parent chain. And notice that there are one, two, three carboxyl group in on the naphthalene. So the others will be the substituents. So there are one, two, three, four substituents. So we name all of the substituents and then arrange them in alphabetical order, and then we get the final answer, which is 1 3 carboxyl propyl, 7 5 hydroxy 3 furan 3 2 pyrazine 2 phenyl 6 indole 4 4 oxazole 5 naphthalene 2 3 6 tricarboxylic acid. And that's all from me. Thank you.
So I will be talking about the physical properties of carboxylic acid. So the first one is its boiling point. So compared to other functional groups such as alcohol, ketone, and aldehyde, carboxylic acid has a much higher boiling point. This is due to its existence as a stable dimer through the formation of hydrogen bond between the molecules. So the molecules in the dimers are arranged quite closely and packed. So when that happens, the hydrogen bond in the molecules or between the molecules are relatively strong. So to overcome that intermolecular force, we need much more energy. So when we need much more energy, we need much more heat to help give it more energy to overcome the intermolecular forces. So the next one is its solubility in water. So the solubility of carboxylic acid is influenced by two factors. And these two factors has something to do with its area of hydrophilic and hydrophobic. So the first one is the size of alkyl group or the number of carbon. So if the number of carbon in the carboxylic acid molecule is less than 5, it causes the solubility to decrease. And why is that? This is due to a much bigger hydrophobic area. So once we have a lot of C in the molecule, the area of hydrophobic is much wider, is much bigger compared to the hydrophilic area. So the solubility of carboxylic acid is decreased. The next one is the number of carboxyl groups. So when its solubility increases with the number of carboxyl groups due to its ability to form more hydrogen bond with water molecule surrounding it. Next is its appearances. A lower number of carbon produces a colorless liquid with a strong and often unpleasant odor. Meanwhile, when it has a higher number of carbon, it produces waxy solids. So now I'll be talking about the chemical properties of carboxylic acid. So compared to other groups, functional groups or molecule, carboxylic acid has the highest strength in acidity, and this is influenced by two factors. The first one is the resonance effect, and the second one is the inductive effect. So, resonant effect happens when an electron in a group can move around, or in other words, delocalize, or spread out over multiple atoms. And this does not just happen due to double bonds. It can also happen due to lone pairs of electrons or in certain groups that are connected to the molecule. So when this happens, when delocalization happens, it causes the molecule or ion to become more stable because the electrons are shared not just by itself, but it shares the electrons across more than just one atom. Yeah, and it helps explain why carboxylic acid um are more acidic than alcohol because in alcohol, the negative charge or the electron can't move around. So when they cannot move around, they're less stable compared to carboxylic acid, where it can move around and it is more stable than alcohol. hence why it is much more acidic compared to alcohol. Next is the inductive effect. So, the inductive effect is the way electrons shift in a molecule due to the presence of certain atoms or groups, and this happens through single bonds or sigma bonds. And inductive effect is influenced by two other factors, which is the presence of EWG and EDG. So the first one is the presence of EWG. EWG is actually electron withdrawing groups. So these groups um, will stabilize the carboxylate ion and increase the acidity by attaching itself to the carboxylate ion. Um, the next one is the presence of EDG. EDG is an electron donating group. EDG will destabilize the carboxylate ion and decreases acidity. Okay, so think of it like a tug of war with electrons. Electron withdrawing groups are like strong players pulling electrons towards themselves. Compared to electron donating groups, they are like pushing players helping to spread the electron density around. Yeah. So that is the function of EWG and EDG. Next is the reaction of carboxylic acid. The first one is its neutralization with a base. So when carboxylic acid is reacted with a base, it forms carboxylate salts, which is commonly used in soaps and detergent. So why is it commonly used? This is because carboxylate salts are water soluble, so it is suitable for the making of soaps and detergent. So the second one is reduction. Carboxylic acid can be reduced to primary alcohol by using strong reducing agents like lithium aluminium hydrate. So it only uses strong reducing agents because milder agents do not reduce carboxylic acid to primary alcohol. So the third one is acid chloride formation. Acid chloride are highly reactive intermediate uh, which is commonly used in organic synthesis. And then the fourth one is anhydrate formation. In this formation, it is often heated with a dehydrating agent. The fifth reaction of carboxylic acid is esterification. So, esterification is where carboxylic acid reacts with alcohol in the presence of an acid catalyst to form esters. And this reaction is a reversible reaction. Um, Esters are commonly used as fragrants, flavoring agents, and solvents. And then the last reaction is amide formation. Carboxylic acid reacts with ammonia or primary or secondary amines to form amides. And in this formation, it requires heat or dehydrating agents. So, as you can tell, we use carboxylic acid a lot in our daily basis. For example, that I have provided in the slide is benzoic, acetic, and aspirin, and a lot more. And so it shows how much importance and benefit carboxylic acid has given us in our daily basis. So that is all from me. Thank you.